So I'm Jordi Blasco. I'm co-founder and CTO of HPCNow. My background is in physics, computational physics, and I have been working in national level HPC facilities over different places and working as advisor, independent advisor in HPC, teaching at the uni, and many other stuff. And so let me go. Quick introduction to HPCNow. It's a global company. We provide services, okay? And this links a little bit on the topic of today. So I will skip the background. If you have some interest, we can talk later about that. So the services that we provide, it's mostly for this topic that I'm introducing. It's consulting, it's administration, remote administration, and remote support, either from HPC administration point of view and a scientific support as well. So I'm going to skip this one as well. So the motivation, it's about identifying opportunities to improve the efficiency, the job efficiency, are quite clear. So probably you are quite familiar on those situations, okay? So you buy a new cluster and you expect to be 100% utilized till the very end of the journey, right? But this is not usually the case. We buy a brand new machine and it takes time to get the jobs populating the cluster evenly, 100% without any delay, without a queue waiting. So this is unreasonable, right? So the reality is quite different. So at the very beginning, the cluster is underused. Then we see a lot of ongoing and hunger to get in there, and people fighting because they want to run more and more jobs. And when you are at the very end of the life cycle of that cluster, probably it's a way to overload. So higher waiting times, hardware potentially no longer supported, or hard to get the replacements of that. Cluster contention, higher demanding workflows. So at the very beginning, you align the I/O subsystem to the I/O patterns that you had at that time. But at the very end, potentially, and this is a trend that we have seen, the I/O patterns change and are more and more demanding. So no longer suitable for handling the massive I/O demanding of those workloads. So at the very end, it's just a risk of using dissatisfaction. So what solutions do we have? Easy, buy a new cluster, okay? So that's traditionally the best way to handle that. So if you have a very strict period of time where you have a new income, new budget to buy a new machine, so that's fine, okay? But the reality is not usually like that, and it usually comes with a lot of overhead as well. To prepare tender, it's quite a painful process. All the people that have been involved in that know quite well about that. So it's not something that you can buy the shop next door, okay? So it takes the time. And the bigger the machine, the more time it takes to get that thing in place. So it's not something that you can do magically like this and get the problem is solved. And it involves a lot of money, obviously. So use the cloud. Yeah, good. So you have a lot of resources in the cloud. You can take advantage of this. We have already implemented cloud busting for some companies, mostly startups, that they have to grow. They don't have capacity to buy a cluster locally or the building to handle that. But the reality is that staging in and out data, what workloads and applications are suitable to run in the cloud, it's something that requires a logic at the workload manager as well. So we have conducted that. We architected that in that way. And we see situations like this. So this is trying to represent the capacity of your local cluster, which can be more or less overload. And then certainly you have a peak of need that can be offload into the cloud. So obviously, if you have to meet the demand of your users, you need a cluster this size. But at the end of the day, this is really expensive. That explains a little bit the economics of taking advantage of cloud busting, right? So it's much more efficient in terms of cost, okay? Total cost of ownership. So, but the topic of today is about improving the efficiency. So this is the other thing that we can do things even better. But what can we do to do it easily, to identify opportunities, to tune, to improve the utilization and the efficiency of the codes? So if we are able to tune a little bit to improve the efficiency, somehow it's like you're creating a new allocation. You're extending the lifetime of the cluster. You are mitigating the demand, the enormous demand that you have now facing in the cluster. So that's pretty much the idea, okay? But how to identify those opportunities easily? The problem is that most of you probably have a Ganglia or similar kind of technology for monitoring. But there's no link to the job. There is no link to the user. So it's just random monitoring for the load, the CPU load, memory usage, and all those kind of things. Definitely there's no link to other nodes allocated that have the same job allocated, or the same jobs in the same workflow, or if it's a job array. So different kind of patterns that you can identify then potentially efficiency difficulties or challenging patterns in there. So what we wanted to achieve is something that can review that reviews the difference between what the users are asking, what they are actually using. We want real-time monitoring because we want to react really quickly. If we see a massive CPU underuse or massive memory underuse, we need to quickly react to that situation and avoid, I don't know, to create more JAMA in the waiting queue. And then the resolution, 30 seconds, it seems quite okay for regular HPC workloads. Not that okay, for example, for more HTC with a very short time frames, but good enough for the first approach, the first iteration, okay? So the architecture, so it's basically, we are considered a lot of metrics, so we need big data strategies. So at this point, we are using Elasticsearch, InfluxDB, and Grafana to represent the data. And this is the traditional stack pipeline, shipping the data from RCS log to the Logstash, and then to the Elasticsearch, and then when the package arrives here, I'm exhausted. So it's too much cumbersome architecture for a thing that should be much easier to handle. So what we did is remove this and ship directly with a custom code data into the Elasticsearch, and then represent the data into the Grafana. So by doing that, so this is the standard, okay? So we have been able to reduce the size of the package from 2,000 to 400 bytes, okay? And so this at the end, it means that per year for a cluster of 380 nodes, we have been able to consolidate. So in the old strategy, in the previous, the standard strategy, it will require like pretty much 2 terabytes. By using the custom that we have developed, it's just a few hundreds of megabytes. And then the theoretical limit of events per second, it blew up. So 260,000 events per second. So it's just, I was really surprised about those metrics as well. So this is how it looks, the dashboard that quickly defines that you have a problem in the cluster. And I would love to provide the demo, but it's usually a kind of sensitive data because what you have here are logins, and it's not good to expose that. And so this is a cluster, 6,000 cores cluster, quite a limited one for the research that they are doing. And as you can see here, there's a huge difference between what the users are requesting to what the users are actually using. That's bad, really bad. So we are talking about in average 72% of efficiency overall. And in addition to that, there were a lot of jobs waiting in the queue. So that situation was terrible when we arrived and we started to work in this site. Okay. So in this, yep.
Is that CPU? Is that time or what is that? CPU?
Sorry. Yeah, from there you cannot see it properly.
I mean, because if they're requesting more time, then maybe that's normal.
So this is CPUs in use versus the CPU requested by all the users. You can select a particular user, and then all the data actually change at the same time. And this is the timestamp and the number of CPUs. Okay. So this is here you have an overview of the CPU efficiency in terms of percentage, and then here you have the users. Oh, sorry. The users that need your help. Okay. So this is a way that we identify. Yes, let's put it this way. So sorry about that. So here you have a timeline time series, and then you have the aggregated view here. So over, I think this is from day 10 to, it's 1 week. In 1 week, this particular user, the user in green, managed to underuse 12 years of CPU time. So,
Does the cluster have GPUs?
sorry?
Does the cluster have GPUs?
No. No GPUs at all. And so when we implement this, because we implement this as a service, okay? So we want to tune, we want to improve things in the client side, right? So we use those tools to instrument what we have to do in order to improve that, to identify those opportunities. This is not a package that you can download, install, and whatever. As you can see in a minute, so the architecture itself, it's quite complex. So it requires to install several software packages to consolidate databases, and then some other services to consolidate different metrics. So it's not that easy. And to automate the process of installations, it's again, so not documented. No, so we are still on the process. Okay, so what I have already shown you, it's something that we have already installed in several sites already, but we want to go further. So the current situation is that we have been able to identify those opportunities, but we want to analyze them at the same time. So, and this is a next step forward. So we want a tool that can be useful for the end users to gain more maturity, to understand what they actually need, and then with this feedback, update the requirements as they go. So in the sites that we have already implemented this prototype that I'm going to show you, we have seen users getting more and more maturity. And this is really good because it comes with less stress on the end user support team. From the end user support team, they have a better tool to better support how the cluster is going, how to interact with the users, and yep, so this is the first step to do so. You can easily correct the workflows. You can detect end user mistakes quite easy. And if this is something that it's more related with the code, then there's a lot of room for the computational scientists to identify those potential problems. And for a computational scientist, and I have been working in this area for quite a big time, it's really, really hard to get the code and run the benchmark, and then profile the application, get all the performance analysis, and finally get the tune, the code update. Okay, so at the end of the day, if you can analyze this data real time, you can more or less identify the needs or get something, what is going on in there, and you can identify the patterns of the behavior of the different tasks, different MPI tasks, and the memory usage, all at the same time. Okay, so this is pretty similar to job profiling. It's available in Slurm, but in a resource manager agnostic way. And then for the platforms team, so all this data can be consolidated in a very nice charts and can tell you what you really need. If you are your users, how much memory and CPUs do you need? They will lie you, literally. And they don't know they are lying you because they don't know, definitely. So with this data, you can more or less guess the trends, because the longer you take this data, you can see more trends as you go, and then you can define the basis for the next procurement, for the next system. So back in the time, so we have been developing this bit for 1.5 years, I think, and involved are all the metrics that we are already consolidated. So this is the wish list that we had at the very beginning. So we want to incorporate instructions per cycle, alerts and event correlation, and also MPI stats, at least for the collectives. Yep.
Are you sampling everything at the same resolution, or
yes.
Like for temperature, you don't need it maybe every 10 seconds because it doesn't change?
Yeah, exactly. For temperature, I don't care too much about that.
Yeah,
but it's not in the list, isn't it? So, sorry, say it again.
Yeah, even with this, I mean, different metrics might need different resolutions.
Yes. So at this time, all those metrics that we have here are collected by 10 seconds resolution. But you're right. So probably we want to have other metrics that can provide alert or event correlation, like a annotation in the Grafana. So this happened, and then you can see what else happened at that time, right? So temperature going up, maybe this is something related with some workloads, or maybe a hardware error or something else. It's good to identify that moment in the time and then see what actually impacted. Yeah, you could, if you know how much consumes every device, yes. Yeah. So actually, David is going to talk about that, and he requested a table with the cost, because the users doesn't need, the users in IXC, they don't pay for it, but they want to show how much it costs to run that simulation. And if you see how much time you spend doing nothing, you can see it's quite sensitive, okay? But sometimes it's really useful for highlighting the importance of doing the right thing. So we are now involved with a project with Cray, and we are providing this monitoring solution, and this is kind of the pipeline, okay? So, okay. And most of the metrics are collected with CollectD, but we also collect, so it's a much wider the scope that I discussed in the previous slide, okay? They want to get data for, based on the applications that they are running, 25, not only the jobs, but the application and the binary run and consuming most of the time, okay? Because if you're using just the model tracking, sometimes it doesn't match with the reality, so the binaries that some people are running. Yeah, so this is pretty much what I have. So I don't have too much time to go in detail, but I'm really happy to talk with you about this in the Chip 2 Blasco Supercomputing Center. And this is how we architected the whole thing. So in order to deploy quickly, Docker as well. We have talked quite a bit about that. So we have a Docker Compose file that pretty much deploys everything. And if you have a need for Docker, for Kubernetes, you can pretty much translate to Kubernetes in one go. And so that's pretty much the architecture and all the minor components that we are using for collecting everything. And the prototype, we go from 8 metrics per user to 318, so it's quite a big. So you need quite a big chunk of infrastructure to consolidate those services. And for a 380 cluster size, so you need around 8.5 terabytes of data per year. And we have already implemented, we're implementing now retention policies on top of InfluxDB in order to mitigate this, because you don't need to get 10 seconds resolution over 1 year. Okay, so that's the point. And if you need to scale up, so those metrics and this data that I mentioned before, it was gigabit based, which is pretty awesome. If you need to scale, migrating to 10 gig or InfiniBand, that's going to increase the throughput. Using buffers will increase the digestion to 10 times, one order of magnitude. And if you need more throughput at the database level, so you can virtually grow unlimited by including more and more resources in there. Okay, so at this time, test that we have conducted doesn't show any performance penalty based on HPL results. The tests have been conducted on, HPL tests have been conducted on 8 nodes, Haswell nodes, and usually when the system is smaller, you see more penalty. So we haven't tried what penalty should be on higher scale, like thousands of nodes and so on. And so here you have some relevant case studies after that, because this is actually to improve the codes, to improve the workloads and to increase the efficiency. But I don't have too much time to go in detail. So what you have here is the CPU time. Going to explain this table a little bit. So this is the CPU time spent after we corrected the issue. And so if you do the math, so this is 4 million, or let me look for something. Yeah, 1 million after we corrected, and we moved from 1% efficiency to 98. You do the math, and you realize that that wasn't feasible on a human lifetime to conduct that. Okay, so this is the reality. So this is the beauty of that. So this is the strength of the tool. And now David is going to introduce to show a few examples of what we have done. So.
Good morning. My name is David del Prado, and I work in Cantabria. First of all, sorry for my English. Okay, if you don't understand anything, you can ask Jordi later. Well, let's go. Cantabria is a okay. It's a research center located in Santander, Cantabria, in the north of Spain. We are ICTS. We are a unique scientist and technical infrastructure. We have this big pool, and it's amazing to see. And the main objective of EH Cantabria is to become a leading international research center in the field of water. That means that we work with everything related to water. We simulate waves, we simulate tsunamis, okay? And before to work in EH Cantabria, I had never worked with a supercomputer cluster. My role was a system administrator. I worked with VMware, storage file systems, networking, security, but I had never worked with a supercomputer cluster by that time. And obviously, we have a supercomputer cluster. This is our cluster. This is Neptuno. Neptuno has 8 nodes, 1,300 cores, 5 TB of RAM, about 30 flops, and 130 storage. It's online since March 2012. It's our cluster, but it's enough for us, okay? And the first contact with the cluster, for me, was like a black hole. I don't have knowing, I don't have administration, I don't have maintenance, and I have a lot of problems, okay? And so for this reason, we contact with HPCNow to today the cluster, and we change everything. We changed the operating system from Red Hat to CentOS. We changed the scheduler from Moab to Slum. We installed modules and NEC build to create friendly environment to the users, to to use the software from the system administrator to deploy new software. Very amazing. We install high-availability services and the suite of Snow. And with all these chains, we have a control and administration about our cluster, okay? And we always use Nagios, and I love monitoring our infrastructure. And in this point, we start to monitoring our cluster. We start to monitoring basic services, the storage, for example, the CPU of load, the pin time, critical services. And the objective of this monitoring was to create alerts. We create alerts to send to emails or, for example, to Slack. But we need more. And the next step was to monitoring the resources. We create a basic script to recollect metrics. For example, this is a output of the basic command like SQ, and we recollect the cores used, the RAM, the storage, and integrate this information in this dashboard in Grafana. For example, in this dashboard, the user can see in percent how many resources are available in this moment, and it's very useful for the users. It's possible to see the state of the queue, how many jobs are running, how many jobs are pending, and very useful, okay? But this is not enough to know the behavior in a cluster. And so for this reason, we contact again with HPCNow, and they propose us to create several dashboards and new monitoring with the behavior of the cluster to see the efficiency and the optimal setup, for example, for the cluster. For example, this is a SDR command. It's very useful to know the scheduler behavior. And we transfer this information about this graph. In this graph, it's very easy to see how many jobs are submitted, how many jobs is started, the state of the queue, the backfill of the cluster, the scheduler. It's very useful to know the behavior. And with this information, we can change the setup of the scheduler to optimal setup, for example. Other written critical for us is the file system. We have a GPFS, and this is a metric with a GPFS read and write, the call request, the inode update, an important item for us is the latency. When we have a high latency, we have a problem of availability and a performance in a cluster. This is a screenshot. It's a real situation about a high value of read and write, and thanks to this dashboard, we detect this problem very quickly because we have alerts in this situation, and we can fix it as soon as possible. Okay. And the efficiency is very important too for us. When you have limited resources or when you have you don't have any money to win in hardware, the efficiency is very important. In this dashboard, you can see the total CPU and users for all our users, or you can see a ranking with the users with more and the user CPU time. You can view the information about all our users. You can filter for one of them. And the blue graph is very important and very easy to assist an administrator because it's the average CPU efficiency in percent. It's very simple because if you don't have a 100%, you have a problem of efficiency. And thanks to the dashboard, it's very easy to detect the problem. For example, in this dashboard, in this screenshot, in only 12 hours, one user have 8 years of under user CPU time. Okay, and in this moment you can detect the problem and you can, for example, kill the user or kill the job. Well, kill the job. and it's very useful. Okay, and sometimes we use reservation. Reservation is the opposite of efficiency. Every time you create a reservation, you have problem of efficiency. But sometimes the user, when the user have deadlines and need resources, the only way to the user be happy is to create a reservation. It's very terrible to see how many resources are wasted every time we create a reservation, but that is useful for us because we have information about this problem. And accounting is interesting for us too. We calculate the CPU per user, per account, per storage, and we can transfer this information, for example, in Europe, and the user can see what is the cost of the project, for example, very quickly. But this is not the most important in the dashboard. In the other graph, you can see the job state, and you can create a relationship about the CPU use by the job state. How the job is fine, is complete. For example, you can see in percent how many jobs in percent are complete, how many jobs are cancelled, how many jobs isn't filed, how many jobs isn't filed because a note is in error, and you can create a report about this information. It's very useful for the company. And this is another example of analytics and about the information of the cluster. This graph is a job distribution. You can see the job size versus the lapse time, and it's a real photography about the job distribution. You can see, for example, a lot of small jobs, and in this point on the right, you can see a lot of jobs for one setup. Okay. And you can say, for example, the information about all of the users or one of them. And with all this information, is very useful for us because we can create reports for the user. This is, for example, is a sample or report to the users with a optimal configuration. When the user have a setup with a file with the setup of course or RAM, for example, and we can create reports, for example, sorry, for example, for the box of the company with what projects are efficient or no. We can create a good decision about the setup of the cluster, or when we need to buy new hardware. We have a lot of information about the requirements about our necessity. Okay, and more or less this is all. Thank you for your time, and bye.
Getting much more with those tools. We are able to early detect user mistakes, increase the HPC maturity on the user community, improve the user workflows, accelerate the research, improve the reliability, and at the end of the journey, improve the user satisfaction. So, this is not yet complete, so this is still a room for improvement. So this is an open call. If you are interested on something like that, if you want to get involved, contact with us, and we can talk on what we can do together as a collaboration. Okay. And that's all. So thank you so much.